board plot. Yesterday I had shared a pic of similar graph sheet. Everyone please keep that similar graph sheet ready. Carry pencil and a scale. Okay. Let us see what is board plot. So it's another graphical technique to evaluate the closed loop system stability for a given open loop transfer function. So the main objective remains same. We need to evaluate the closed loop system stability for the given open loop transfer function. So it's more or less similar to the Nyquist plot, except the scale on which we represent the system frequency response. So Bode's plot is also the frequency response of the system, but we are using a similar graph sheet to represent the frequency response. So it's logarithmic scale. We call it as a logarithmic scale. So I will straight away move on to the uh, steps of drawing the board plot, and there is no much theoretical background for this. So you need to follow the steps whatever I give it for drawing the board plot. And before that, please remember these key points or the key terminologies for drawing the board plot. So first one is a pole contributes a slope of minus 20 dB per decade. Just listen to this. Once we start solving, we will follow it. A pole contributes a slope of minus 20 dB per decade, and a zero contributes a slope of plus 20 dB per decade. Then identify the corner frequencies. Okay, the corner frequencies is a new terminology. dB per decade is a new terminology. We'll see to it what are these terminologies mean. Then the next one is in the board plot there are two plots. First one is gain plot, second one is phase plot, and both are drawn in the same semi-log sheet using two different scales. Okay, so these are the key points to remember. So let me start straight away with a numerical. Investigate the stability of closed loop system for the given open loop transfer function, that is g of s into h of s equals to 50 divided by s into 0.5 s plus 1, then 0.05 s plus 1. So this is the given transfer function, open loop transfer function, for which you need to check the closed loop system stability using Bode's plot. So there are three poles and there are no zeros. So how to proceed? We need to use this semi-log graph sheet. The semi-log graph sheet for representing the Bode's plot. Everyone please take out your sheet. Keep it ready with you. Keep the graph ready with you. Ganesh, can you view this PDF?
Yes, sir.
Yes. So you need to mark all these. Okay, I need to rotate this. Just 1 second. So this is how it looks like. So this is called x-axis, and it is for representing the frequency in radians per second. Okay, the frequency omega. So while drawing, make sure that there is a count written on the semi-log sheet as 1, 2, 3, 4 up to 10, then 10, 1, 2, 3, 4 up to 10. So it's been printed there, but we have to use that scale as each solid line represents a decade change or a change of 10 times in the frequency. So this is a first solid line. I will choose this first value as zero point 0.1 omega radians per second. The next solid line represents a decade change or 10 times change, which is zero point 0.1 into 10, that is 1 radians per second. Then 1 into 10, next solid line 10 radians per second. Then 10 into 10, 100 radians per second. 100 into 10, 1000 radians per second. And the last one to be 10,000 radians per second. So this is frequency scale. And in between these solid lines, there are other lines which represents the frequency. So after 1 radians per second, 2 radians per second is this line, 3 radians is this line, 4 is this line, 5, 6, 7. So this is logarithmic scale. They are not equidistant. So with this, we will go to first gain plot. So gain plot is nothing but drawing the gain of the open loop transfer function. So we have already seen how to write the expression for gain in an equidistant plot. So that is gain of g of s h of s or gain of g h j omega equal to square root of something something. Okay. So that is nothing but gain expression. And for each frequency, we will plot the gain plot here. So we'll see next. So this left side y-axis is chosen as gain in dB. Gain in dB. So each solid line I have chosen for 20 dB difference. So first line baseline is 0 dB. Next solid line plus 20 dB, plus 40 dB, plus 60 dB. You can change these values according to your requirement. You can change the scale. You can change the scale in the sense uh, like suppose see imagine you if you want it for 40 dB, 80 dB, 120 dB. Okay, but this slope whatever I have drawn, when you write 40 dB here, this is no more a 20 dB per decade slope. This will be something else. But for drawing board plot, we should have a reference of a slope of 20 dB plus 20 dB per decade or minus 20 dB per decade. But most of the numericals will never cross the maximum value 60 dB, so no need to change the scale. So please keep in mind and avoid confusions. Use the same scale for all the numericals. Right? Next, this is 20 dB gain, and if I draw a line from plus 20 dB to this point, it is a negative slope line. Okay, it is a negative slope line. And to be specific, it is written as the line with the slope of minus 20 dB per decade frequency. Okay, it's line with a negative slope of minus 20 dB per decade frequency, because per decade is written because the x axis is having a distance of a decade frequency. Right? So this is the standard way of starting the board plot. Please don't make any changes in any of the numericals. Okay, keep this standard. So similarly from 40 dB to this 1 radians per second, there is again a change of decade frequency. Again a negative slope, but it is from 40 dB now, therefore it is minus 40 dB per decade. Similarly, minus 60 dB per decade. Then when you draw a line from minus 20 dB on the negative axis, it is an increasing slope. Okay, it is an increasing slope, therefore it is plus 20 dB per decade. Similarly, this is plus 40 dB per decade. So these are the standard lines we need for reference. Then coming to the phase plot, for drawing the phase diagram, which is phase angle of g of s h of s, I use the y-axis of right hand side of the graph. So on that y-axis, I represent the phase angle. Okay, phase angle minus 180, minus 160, minus 140, minus 200, minus 220. So this is negative scale. That's why minus 40, minus 160, minus 180, minus 200, minus 220. So even this scale can be changed according to our convenient. So I suggest that keep the gain scale for the gain plot same as shown here, but for phase plot you can change accordingly. Okay, so you can start from say minus 100, minus 150, minus 200, minus 250, minus 300. Okay, like that you can change for the phase plot, but don't change the gain plot gain scale. So this is phase angle in degrees, this is gain in dB, and I have taken minus 180 degree as a baseline, and I will tell you why it is chosen, why this one is specifically chosen as a baseline for phase plot. So that's it. In the Bode plot, there are two separate plots. One is gain plot, another one is phase plot. For gain plot, these are the reference lines, standard reference lines, and for phase plot, minus 180 degrees is the baseline. So I hope there are no difficulties in this. So I'll straight away move on to the numerical. So I'm skipping this part now because I had given you the information. Please do not look at this graph as of now. Ignore the graph. So step 1 is identify the starting point of the gain plot by considering the pole at origin or zero at origin. Okay, identify the starting point of the gain plot by considering the pole at origin or zero at origin. Since this is a first numerical, you will face or you will feel some difficulty. Once I solve 2 to 3 numericals, things will be very familiar and it is a very easiest technique. It's not as difficult as my quest case. So step 1 is identify the starting point of the gain plots. So how to find the starting point is just substitute s equal to j omega in our open loop transfer function. So it is 50 by j omega into 0.5 j omega plus 1 into 0.05 j omega plus 1. 0.05 j omega plus 1. So next is to find the starting point. Let us look at to find the starting point. Let us look at the x scale. X scale is which is the frequency scale and it starts at omega equal to 0.1 radians per second. Okay, so our x scale is starting from omega equal to 0.1 radians per second. So our plot begins from this axis and moves towards the right hand side of the graph as the frequency changes. So that's why I call the starting point will be at omega equal to 0.1 radians per second. So when I choose omega equal to 0.1 radians per second, I can find the starting point. So how to find the starting point? Let us choose a pole at origin, which is nothing but 50 divided by s. This is pole at origin. It is nothing but s plus 0. So that's why I call it as pole at origin. So I will choose only that term which is having pole at origin. So 50 by j omega is the term. So now what is the magnitude of 50 by j omega? It is 50 divided by square root of omega square, which is omega. So 50 by omega is the gain of this term. So if I apply log to this scale, log to this expression, that is 20 log y f j omega, then I will get 20 log 50 minus 20 log omega. So this omega will be 0.1 now. So 20 log 50 minus 20 log 0.1. What is this value? Use your calculator, please. 20 log 50 minus 20 log zero point 0.1. This is equal to 54 dB. So 54 dB is the starting point for the gain plot. So at this point of time, you may have different questions like you feel why 20 log is applied, why 20 is applied, why not only log, why only this term is chosen. Okay, so there will be a number of questions, but I feel that those things are irrelevant. Okay, understanding those things are not necessary actually, because it doesn't require any much theoretical background. This Bode's plot doesn't require much theoretical background. If you have understood the theoretical background of Nyquist plot, that's more than sufficient. Okay, so while analyzing the system behavior in frequency domain, most oftenly we use Nyquist plot or the logarithmic scale of Bode plot. That's it. So the theoretical background or the conceptual background remains same for both Nyquist as well as Bode. And one more thing is, Bode plot can be interpreted as the rapid technique for Nyquist plot. Okay? A rapid technique for Nyquist plot. That's why that scientist Bode suggested some modifications with the Nyquist, and then he proposed that on the logarithmic scale, which will reduce the computational time as compared to the Nyquist plot. So that's the only difference. So don't have much questions in the mind. Just listen to whatever I say. So this is starting point of 54 dB and starting point of 54 dB. So now how to locate that starting point? So can you say we finish this graph?
Yes, sir.
Yes. So everyone please mark the starting point, the approximate point 54 dB here. Okay, on the y-axis. So 40 dB is here, plus 40 dB plus 60 dB is here. So 54 dB is approximately somewhere here. So just put a dot and write down 54 dB. Then we will proceed with step 2 of the gain plot. This is starting point of the gain plot. Step 1 is done. Step 1 is about gain plot. Next, move on to step 2. So step 2 is very easy, and at a stretch we will finish the gain plot. So let us see how it goes. Identify the corner frequencies in the increasing order and add the slopes cumulatively. So what does this mean? What is corner frequency means? Okay, so please remember this. Pole is minus 20 dB per decade and a 0 is plus 20 dB per decade. I will make a small table. I'll write the factor, then corner frequencies, then the net slope. So how it goes? The first factor we chose as j omega, 50 by j omega. So I will call it as a first factor, and using first factor, which is a pole, because s is present in the denominator, we call it as a pole. So for the first factor, there doesn't exist any corner frequency. Okay, and the net slope for a pole, as I have shown in the previous slide, the net slope for a pole is minus 20 dB per decade. So this is the first row of the table. First row of the table, you write the first factor, check out whether it is a pole or a 0. Suppose if it is 50s, then we call it as 0. Since it is 50 by s or 50 by j omega, we call it as a pole. So pole contributes minus 20 dB per decade. What is the next factor? So the next factor has to be chosen such a way that we get the corner frequency in the increasing order. So let me see what is that corner frequency. I have written something here. 1 divided by 0.5. Omega 1 equal to 1 divided by 0.5 is a corner frequency. So from where this 0.5 has come, so let us see. So it has come from another factor of the transfer function, which is 1 divided by 0.5 s plus 1. So there was another factor which was multiplied with this denominator. So that is nothing but 0.5 s plus 1 or 0.5 j omega plus 1. So from this I have chosen omega 1. Okay. So omega 1 equal to 1 divided by the coefficient of s. Okay, the constant that is multiplied with s. So it is 1 divided by zero point 0.5 equal to 2 radians per second. So let us see what is net slope for this. Yeah, this is here. What is net slope for this term? So net slope is given as previous slope plus the present slope. Present slope, that is the slope contributed by this factor. So what is the previous slope? Previous slope was minus 20 dB per decade, and the present slope is by the pole. So pole also contributes minus 20 dB per decade. Net slope is minus 40 dB per decade. And the third factor I am choosing omega 2 as 1 divided by zero point 0.05, which is equal to 20 radians per second, and it comes from the third factor in the denominator, which is also a pole. Okay, which is also a pole. So you can now guess what is meant by increasing order. So to make the table like this only, you have to identify the factors carefully. Okay, just by calculating roughly somewhere which one is having the lowest corner frequency. That should be chosen first. Then next is the next highest. So 2 is the lowest. I have chosen this factor. Then 20 is the next highest. So I have chosen this factor. So what is the net slope for this? So net slope for this is again previous plus present slope. That is minus 40 is the previous slope, minus 40 dB per decade, and the present slope is slope contributed by this pole, that is minus 20 dB per decade. So altogether it is minus 60 dB per decade. Fine. So this is the calculation. Please have a look at this again carefully. So step, once you identify the starting point, next step is to proceed the graph on the frequency scale. So for that, this is the table we should follow. In that, first factor is always pole or a zero at origin. So it doesn't have any corner frequency because it is starting from omega equal to 0.1 radians per second. So looking at the factor, you write the slope for that. So if it is a pole, it is minus 20 dB per decade. If it is a zero, it is plus 20 dB per decade. So next, identify the corner frequencies in increasing order and name that particular factor, whether it is a pole or zero, because it can be present in numerator also, in denominator also, in the given transfer function. But as of now, it is present in the denominator. Therefore, we have a pole and the corner frequency is 0.5, 1 divided by zero point 0.5, 2 radians per second. And the net slope is previous plus the present. So minus 20 was previous, minus 20 contributed by this. Therefore, it is minus 40 dB per decade. So similarly for the third factor, both are increasing in order. So how to proceed next? Everyone please carry a scale. Please carry a scale. And I will show you how to draw the line, how to proceed for the graph. Fine. Okay, so take a scale and choose the starting point. Choose the starting point and mark the corner frequencies. So you can mark the corner frequencies as shown. See, 2 radians per second is the corner frequency, so I have marked 2 here. Next, 20 radians per second is the corner frequency, so I have marked 20 here. Everyone please mark the corner frequencies. Just mark on the x-axis, not here. Not here. Just mark 2 and 20 here. So after this, what is the next step? The next step is in the table. Look at the table. Our first factor is having a slope of minus 20 dB per decade. Okay. So minus 20 dB per decade. Therefore, what you need to do is take the scale, and take the reference of minus 20 dB per decade line. Take the reference of minus 20 dB per decade line and draw a parallel line to the minus 20 dB per decade from 54 dB. Okay, with the same slope. With the same slope. So it should be parallel to minus 20 dB per decade with the same slope. So till what point you need to draw this? till what point you need to draw this is up to next corner frequency. Up to next corner frequency. So 54 dB was the starting point, and till 2 radians per second, our slope will remain minus 20 dB per decade, which is parallel to this line. Wait for 2 minutes. If anybody has not understood, you can ask. Draw only the first line, whose slope is minus 20 dB per decade up to first corner frequency. Shravani, have you understood? Aditya Raj, Darshan GK.
Yes, sir. I'm finding it a little difficult, but I'll rewatch the video, sir.
Okay. Keep a graph sheet parallel to it.
Yes, sir.
Darshan, Falak.
Sir, I have to rewatch the video.
Okay, fine. Okay, we'll proceed now. So once you draw a line with a slope of minus 20 dB per decade from the starting point, stop at the corner frequency. So next is after 2 radians per second, the net slope is minus 20 minus 20, that is minus 40 dB per decade. So after 2 radians per second, after 2 radians per second, you draw another line which is parallel to minus 40 dB per decade. So it goes something like this. After 2 radians per second, this line is parallel to minus 40 dB per decade. So use the scale and move accordingly. So till what point? Till next corner frequency. So the next corner frequency was 20 radians per second. So till that point, you draw the line with a slope of minus 40 dB per decade. So hold the scale, move it parallelly, and draw the line up to 20 radians per second. That's it. And after 20 radians per second, it is the net slope is minus 60 dB per decade. So now hold the scale parallel to this and move slowly and draw the line of minus 60 dB per decade like this. And there is no next corner frequency, so you can leave it as it is. Okay, you can leave it as it is. No need to move it beyond the graph. So what is important for us is the point at which it crosses 0 dB. So that's the only important thing for us in the gain plot. Okay, so I repeat again, from minus 54 dB, check what is the slope. If it is a pole, it is minus 20 dB per decade. So hold the scale parallelly and move it here and draw a minus 20 dB per decade line till the next corner frequency, and from next corner frequency check out the next slope and use the scale and move it parallelly and draw the next line up to next corner frequency. The procedure will repeat. So that is the gain plot.
Sir,
Yes.
sir, in j omega, if it was a j omega square, like if it was s square, then slope will it be minus 40 in the initial?
Yes, because s square is two poles.
Okay.
Two poles at
Sir,
origin. Since this is starting numerical, I have chosen only with one pole. But you can have two poles at the same location, then it will be double the slope.
okay, sir.
Okay, that's why I said a pole contributes minus 20 dB per decade, and two poles at the same location contributes double the slope. That is minus 40 dB per decade. Okay, so with this, gain plot is done. Then we will move on to quickly the next part, that is phase plot. So how do we write the phase angle expression? So phase angle expression is written by looking at all these terms. So the phase angle of omega is tan inverse of omega by 0, and if it is taken to the numerator, it is minus tan inverse of omega by 0, which is minus tan inverse of infinity minus 90 degrees. So like that you can write for all the remaining terms. Okay, so this is the phase angle expression. So for calculating the phase angle, we need to construct a table. We have to construct a table. Yes.
Sir, in the question, if zeros were there, then will the slope for it be plus 20
Yes,
dB, sir?
plus 20 dB per decade. I'll solve that type of numerical also in the next class.
It will be added to previous slope.
Yes, it should be added to previous slope. So this is how the phase plot goes. I will decide the omega values. So this is actually like you need to use your brain. You cannot randomly decide omega values. There is a trick here. So I will tell it now. So for
Sir,
yes.
sir, we randomly add to the previous slope, or we had to add the pole slope to the another pole slope only?
So previous slope in the sense you will start first from either pole at 0 or 0 at sorry. First step is you need to consider pole at origin or 0 at origin. That will decide the first slope. Okay.
Okay, sir.
Next is you need to find the corner frequencies in increasing order. So this corner frequency may come from a pole or may come from a 0. Suppose imagine we have this factor in the numerator. This is 0. Correct?
Yes, sir.
So when it comes from a 0, the present slope is plus 20 dB per decade. And when you add it minus 20 with plus 20, it becomes 0 dB per decade. So your net slope is 0 dB per decade. So where you can check the 0 dB per decade? Where is 0 dB per decade line is present? It is this line.
Yes, sir.
I think I have shared in the notes. You can observe it carefully. So that is 0 dB per decade. That's how you have to go on adding. There is nothing called random here. Okay.
Okay, sir.
So once you calculate the phase angle by substituting different omega values here, you will get these values. Okay. So I've written a comment here, at least 10 values around omega p. So omega p we had defined as phase crossover frequency in the Nyquist plot, and let us see what is omega p, the phase crossover frequency in Bode plot. So observe this particular reading. The value from 6 to 7 shows that the phase angle has changed from minus 178 to minus 183, which means that between 6 radians per second and 7 radians per second, some value will show you minus 180 degree. Okay, minus 180 degree. And if it is possible to calculate, it is fine. If it is not possible to calculate, just highlight these two frequencies and understand that the phase angle cuts minus 180 degree line only between these two frequencies. So if that is the case, that is well and good. So once we calculate the phase angle, we need to mark it on the graph. So how do you mark it on the graph? So at omega equal to 2, the phase angle is 140. So how do we do it on the graph sheet is, we take this graph, this actual graph, then at omega equal to 2, you put the first point, that is minus 140 degree. Then similarly, at omega equal to 3, we have minus 154, then minus 164, then minus 172, and minus 178, minus 183. So similarly, we will proceed with marking those points here. Okay. So around between 6 and 7, it has cut the minus 180 degree line. Okay. So after that, just 2-3 points are sufficient. So whenever the phase plot cuts minus 180-degree line, we call it as phase crossover frequency in the Bode plot. And whenever the gain plot cuts the 0 dB line, we call it as gain crossover frequency. So these terminologies we had came across even in the Nyquist plot. I repeat again, whenever your the phase plot cuts the minus 180-degree line, we call it as phase crossover frequency. And whenever our gain plot cuts the 0 dB line, we call it as gain crossover frequency. Fine. So this is the scale for phase angle, this is the scale for gain. So once we are done with that, next is checking the stability using the Bode plot. Checking the stability using Bode plot. So how do we do that? First, let us define gain crossover frequency. So it is a frequency at which gain cuts the 0 dB line. Gain plot cuts the 0 dB line. And similarly, phase crossover frequency, where phase plot cuts minus 180-degree line that I have shown you. Fine. So next is we need to find gain margin and phase margin. What is gain margin? There is a definition for it. So gain margin is equal to 0 minus gain at omega p. Gain at omega p. See here. Gain at omega p in the sense you need to draw a line from omega p and check the corresponding gain. So it is around 18 dB. Then we need to check phase margin. So there is again a definition for phase margin. So what is that definition? It is 180-degree plus phase at gain crossover frequency. So this is gain crossover frequency. And what is the phase angle at gain crossover frequency? So plot a vertical line, then check the phase angle on the phase angle scale. So at omega g, is it around say minus 190 degrees or say minus 190 degrees or minus 195 degrees around approximately. So at gain over frequency, this is the phase angle. So what is the phase margin? Phase margin is minus 10 degrees. Okay, so gain margin is 0 minus gain at omega p. Phase margin is 180 plus phase at omega g. So I'll show you once again. So gain margin is 0 minus gain at omega p. So this is omega p. Look at the gain here. So gain is around 18 dB. 0 dB here. Maybe 8 dB. This graph you may not get the accurate values. There will be say possibility of plus or minus 30% error, but the final result will remain same. So for gain margin, if I check the gain value at omega p, it is say plus some value. Okay, plus 10 you can say. Phase margin is 180-degree plus phase angle at omega g. So at omega g, it is around minus 190 degrees. So if you substitute those values, finally we get gain margin negative and phase margin also negative. Okay. So the conclusion is for stability, what is the conclusion? So the present example, the closed loop system is unstable because for stability, both gain margin and phase margin should be positive. That's it. So that is the conclusion of Bode plot. It's a very simplest diagram. You may end up in confusion only at these two parameters, but remember this formula, simple formula. See, you may get an error of plus or minus 30 to 40%. I mean, some may get say minus 18 dB, some may get minus 8 dB, but nobody should get a positive value, okay, which is an error beyond 50%. So similarly, you may get a different phase margin, minus 20 degree, minus 5 degree, minus 12 degree. All are acceptable, but it should remain negative, which is evident from the graph. So for the present numerical, since both are negative, system is unstable. And for stability, both gain margin and phase margin should be positive. It means if you end up with a positive gain margin and negative phase margin, system is unstable, or a negative gain margin, positive phase margin, system is unstable. So both should be positive for stable system, I mean closed loop stability. So that's it for today's class. I have shared notes. Please refer the notes. Okay, that is sufficient. And each numerical takes 1 hour to solve it. I mean in the class. So what I'm going to do is I will neatly write the notes for different numericals. Please go through it before attending the class. And in the next class onwards, I will explain only the notes. I will not draw the graph live because it consumes a lot of time. Please cooperate. We are about to end the syllabus. One more chapter is left. Since this board plot is quite easier as compared to Nyquist plot, I have spent much time on Nyquist plot. So we'll finish off the board plot as quick as possible. So I'll be solving 3 to 4 numericals by Saturday or next Monday. Then we'll jump on to the 5th unit, which is more of theory. Okay, which is more of theory. And for 5th unit, I will be providing the notes also, and parallelly we'll have a discussion also. So thank you. Bye.